Skew groups in VLSI clock tree synthesis, CTS, showing the question. The question you asked dives into an important concept in VLSI design, skew groups. In clock tree synthesis, CTS, skew groups play a crucial role in optimizing the clock tree for balanced signal arrival times. What is skew? Clock skew refers to the variation in arrival time of the clock signal at different points in the design. Ideally, we want all flip-flops, registers, to receive the clock signal at nearly the same time for proper circuit operation. However, due to factors like routing length and cell delays, there can be slight variations. What are skew groups? Skew groups are essentially collections of clock sync pins, typically flip-flops, that are grouped together based on their desired timing relationships. The CTS tool uses these groups to optimize the clock tree by balancing skew within a group. The CTS tool prioritizes balancing the arrival times of the clock signal within each skew group. This means minimizing the variation in arrival times among flip-flops within the same group. Ignoring skew between groups, the CTS tool might not prioritize balancing the arrival times between different skew groups. This allows for some flexibility in the overall clock tree structure. Benefits of skew groups. Improved timing closure. By focusing on balancing skew within groups, the CTS tool can achieve tighter timing constraints more efficiently. Reduced clock tree complexity. By strategically grouping clock sinks, the CTS tool can potentially create a simpler and more routable clock tree. Power optimization. Simpler clock trees often require fewer buffers, leading to potentially lower power consumption. Types of skew groups. Simple fan-out tree. A group of flip-flops driven by the same clock source, potentially with some intervening buffers and logic gates. Integrated clock gating, ICG, cells. Grouping the clock pin of an ICG cell with the flip-flop it controls ensures proper timing relationships between the clock gating functionality and the flip-flop operation. Defining skew groups. Manual definition. Designers can explicitly define skew groups in the CTS tool using commands or scripts. Automatic grouping. Some CTS tools might offer automatic skew group generation based on clock net topology and logical relationships. Conclusion. Skew groups are a valuable concept in CTS, enabling the creation of well-balanced clock trees that meet timing requirements and optimize power consumption. Understanding their purpose and how to define them effectively is crucial for achieving robust clock distribution in VLSI designs. Addressing 300+ shorts in a VLSI design, showing the question. Encountering 300+ shorts in a VLSI design is a significant challenge. Here's a breakdown of potential approaches and considerations for fixing them. Initial analysis. Short type identification. The first step is to understand the nature of the shorts. Are they metal-to-metal shorts, shorts between different layers, wire shorts, or shorts involving power or ground rails? Identifying the type of shorts can help guide the debugging process. Automated diagnosis tools. Utilize built-in features in your design environment, e.g., Cadence Virtuoso, Synopsys ICC, or dedicated shorts diagnosis tools to automatically locate and categorize the shorts. Potential repair strategies. Physical repair. If the design allows for physical access, e.g., packaged chip with bond pads, techniques like laser ablation might be employed to remove the unwanted connections causing the shorts. However, this is usually a last resort due to cost and potential damage. Design modification. Depending on the location and severity of the shorts, consider design modifications like rerouting signals or adding buffer cells to isolate shorted nets. This approach requires careful analysis and verification to ensure functionality remains intact. Redundancy-based repair, if available. Some advanced design methodologies incorporate redundant structures, e.g., spare rows, columns in memory, that can be utilized to bypass faulty connections. This approach depends on the specific redundancy mechanisms implemented in the design. Iterative debugging. Fix and rerun simulation. After implementing a potential fix for a group of shorts, rerun simulations to verify if the issue has been resolved. This iterative process continues until all identified shorts are addressed. Alternative considerations. Scrapping the design, worst case, in extreme cases, if the number of shorts is overwhelming or the location makes repair impractical, scrapping the design and restarting might be necessary. However, this should be a last resort after exploring all other options. Prevention strategies for future designs. Rigorous design rule checking, DRC. Employ robust DRC tools during the design phase to identify potential layout violations that could lead to shorts during fabrication. Careful layout techniques. Utilize proper spacing rules, wire placement strategies, and power, ground planning to minimize the risk of shorts during the layout stage. Advanced design for manufacturability, DFM, techniques. Consider incorporating advanced DFM techniques like corner rounding or double patterning that can further reduce the risk of shorts in complex designs. Conclusion. Addressing 300 plus shorts in a VLSI design requires a combination of analysis, repair strategies, and potentially design modifications. Utilizing automated tools, iterative debugging, and careful analysis are key. However, implementing robust design rules and DFM techniques during the design phase can significantly reduce the likelihood of encountering such a high number of shorts in future designs.